So Tyler, if you don't mind, while we have a minute here, do you mind telling me a little bit more about what happened? You said there was like a 90-person limit or something like that. We were crossing that.
Yeah. So, I mean, I just mentioned this. So I thought that we were going to have maybe 10 people show up to the meetup, and we could, go out for coffee at Stanford, right? To one of their cafeterias, and nobody would, suspect anything. But 90 people RSVP'd, and I was like, this going to be a huge group. They're going to kick us out. So I just put it online, and so that's what we're doing for right now. And hopefully the next meeting will be in person.
More the merrier. Well, good to hear.
Yes,
Always good sign.
I agree. I like having a big old crowd. All right, so it is 2:05. I'm going to keep letting people in as they arrive. But Foka, why don't you take the helm and show us about seaplane.io?
Yeah, definitely. I'll try to keep the sales stuff away as much as I can, and just show you the demo app that I built. And I'll share my screen here, which I have a brief presentation, and then I'll actually do the actual demo. So Tyler and I connected I think it's got to be almost 2 months ago, when we were going through a little bit of a pivot at Seaplane.io, and we started to focus more on data science. Since then, we've spoken to about 200 data scientists trying to understand, okay, what's the biggest problem when you deploy your pipelines? And at first we heard one person complain about infrastructure, and then one more, and then one more, and they just kept coming. And so we're like, that's what we need to solve. That's the problem that we need to solve with the platform that we were building. And so we kind of pivoted in that direction. So what I'm going to show you guys today is how I'm using that platform that we built to create a PDF summary pipeline using the Seaplane platform, but then also GPT 3.5. So it makes a call to OpenAI to make a summary of whatever PDF you put in there. So first, a little bit about Seaplane. What we actually are is we've built a Python SDK that allows you to spin up infrastructure. Think about containerized workloads, but also API, gateways, databases, vector databases, anything that you need for your AI data science apps, without actually having to understand the underlying infrastructure. So it's all Python code, and then it just spins up the infrastructure for you. That's all I wanted to say about Seaplane. Now we'll dive into the actual stuff and actually into the demo. So what I built today was a PDF summary application that's available at an API entry point at /demo input. Then there's a pre-processing step in there that downloads and extracts the text from the PDF and creates the prompt for GPT 3.5. There's an inference step in there, and then there's a database step in there where we store the results in a SQL database. All of these steps are individually scaling serverless containers that we've deployed globally on our multi-cloud resources. And you'll see at the end of the demo how easy it is actually to do this. I'm super hyped about this because I'm just seeing all the possibilities of the applications that you can build yourself. And I hope you guys like it as well. So let me dive in a little bit more. The way we define our applications is through a directed acyclic graph.
Oh, Foka, I think Darshil has a question.
Oh, I see a hand. Yeah, sorry.
Definitely. Yeah, so I had a really quick question. Like, what are you using to extract text from the PDF? I mean, are you just extracting the selectable text, or are you doing some kind of OCR to extract even the?
No, I'm just using PyPDF too at this point.
Okay.
Yeah, but I'll get to the code samples in a bit. So I'll just show you guys real quick. So if you're familiar with Airflow, you're familiar with the concept of a DAG. A DAG is a directed acyclic graph that essentially defines the way that individual components are connected. So in my case, I have an API entry point, like I said, goes into pre-processing, then goes into inference, and then ultimately stores it in a database. So how do you build that? Well, we've created that SDK that as I said, and we're using decorators. Again, very similar to Airflow, if you've ever used that before. You can define an application, which is the actual pipeline where the individual task components fit into. Through the app decorator, applications can be available through HTTP, Kafka, cron job, or other entry points. In this example, I'm using HTTP. And then tasks are the individual scaling components that we fit inside that pipeline, defined through the add task decorator. And with tasks, you can add resources like a SQL database, a vector database, object stores. We've got a couple large language models, open source models that we're running that you can play with, and we're adding stuff every day just based on the things we hear from our early testers. So let's actually start building. Here are the code snippets that you've all probably been waiting for. So this is the app definition. So as you can see here, I shouldn't have clicked. I import the Cplane SDK, our app component, and then I can quite easily construct an app here that's available at demo input through a post request, and I'll just give it an ID so that I can identify it later. And then inside that app, I can wire together different components that we're going to construct later. So what you see here is that my pre-processing takes the body, which is the HTTP body request from the user, and then runs it through that function. And the output of that goes into the inferencing step. And then the output of inferencing, which is the summary, goes into the database. And then at the end of the file we call start, which actually starts the application once we do the deployment. And then the individual components. So we have a pre-processing task. This, like I said, downloads the PDF, extracts the text, and then creates the prompt. I know somebody was asking about how we get the text from the PDF. I cut out that part because it's just rather uninteresting. It's just a GET request to download the PDF and then use PyPDF to extract the text. So I cut out the code in between here just to make it a little bit more accessible and readable on a slide. But as you can see, you define a task, you give it a type, which in this case is a compute. So that means it's a serverless compute container that we're going to spin up. And we're passing in the data component. The data component is whatever we put in here, right? So in this case, it's the body. In the next step, it's the prompt. That was the output of this one. And that data component is a JSON object where you can get the different variables from. We then construct a prompt, and then we'll pass it along to the next step. So in this case, this output is what's going to go into the inferencing step. Inferencing step, pretty similar. So what you'll see here is we've defined a task. I've added a model here, which if you remember from the app step, I've defined my API key for OpenAI there. And so we take care of all the interactions with OpenAI here. In this case, I'm using GPT 3.5, but like I said, we have GPT-30B deployed, BloomZ, we got BloomZ chat deployed as well, regular Bloom. Those are all models that you can simply add by just adding them here, and then they become available as the model parameter here. And then with the parameters object, you can call that model without actually having to set up all these models yourself. And the nice thing about this, or what I'm super excited about, is that, for instance, something like BloomZ and Bloom is about $250,000 a year to run. What we enable with this SDK right now is that you can use it as a shared resource. And so you can try out all these different LLMs and kind of play with them yourself and see how they work. I've been testing GPT-30B myself for the last 2 weeks, and it's, I would say, like 90% comparable with GPT 3.5. It's doing really well. We had to do a lot of tweaking to get it to that level. Like if you just deploy it yourself, the performance is kind of going to suck, and you got to do a lot of prompt engineering to get good results. But right now, it's actually running really well, and we've got a couple of customers that are swapping out OpenAI for GPT-30B for security reasons, but also for cost reasons, because we can run GPT-30B, I believe, for $2 a day, which is a lot cheaper than if you do a ton of calls on OpenAI. So again, we run that, and then we pass the actual result, which is in our case the prompt and the result of the model output. So the summary of the PDF that we asked it to create, we pass that to the next step, which is the last step in our application, which is the database task. We talked to a bunch of people, and I don't think I have ever heard anybody say that they like handling SciCog or like handling database requests. And so what we try to do is hide all the complexity of a database behind the SDK. So all you do is create a SQL Access object and pass that as a resource to the task here. And once you do, that SQLDB object will handle all the connection pooling, anything, the cursor, anything that you actually need to do to interact with the SQL database. It will handle it for you. So all you do is SQLDB.insert, and you just run your query, and then we put it into that database. And that's it. Then it's in our database. So I actually have it deployed. I have once you do the deployment step. So what you do is you go into your terminal, and you run cplane deploy into the main directory. And this is actually going to set up all the infrastructure. So it's going to create 3 different containers. It's going to wire them all together with a data stream in between. It will set up and configure the database, and everything that it's deployed is scalable, serverless, and it's deployed on multi-cloud infrastructure. So we currently deploy, I believe, on AWS, GCP, and Azure, but we also have a couple bare metal providers there to really get the best performance there. Wherever your users are, get the best local performance. Deployment is super quick. I will try to do it live, but we are in beta, so just in case we're going to hit the demo effect, I also have a recording where you can see how it actually works. But I'll let me see if I can stop sharing here. And can you guys see my terminal screen right now, or did I just share my Chrome window?
I can see your terminal.
Okay. Perfect. So inside my terminal here, I have my project, which is the PDF summary. There's a couple other files that I didn't really wanted to touch on. There's like a PyProject.toml that just has the required packages. We use Poetry to install some of these packages. But all you got to do here is then run cplane deploy, which will then start the deployment. It's going to authenticate with cplane using that API key, using the OpenAI API key that we used. And then it's going to start to deploy the actual individual containers. And there we are. It's deployed. So what you have now is a data-driven API where the API gateway is set up that you can talk to with that same API key that we use to deploy our app. So I can fire off a simple curl request that's going to request a token and then call that demo input API endpoint that we have right here. And once it does that, we're going to get back a request ID, says it's status processing. And then if I go into my, let's see, in my database here, we'll see, let's see, select, select, I believe it's called summary from PDF. Summaries. Let's do limit 1 to not overflow my window. And there's the summary of the PDF. That was it. That was the demo. If you guys have any questions, I'm definitely willing to answer. I also came here with, if I can go to the next slide. If you guys want to sign up and try this yourself, I talked to our team. We have some spaces available in our beta. So if you guys want to try, you can scan the QR code. And we have a special offer because we just like you guys so much. So if you sign up and you put any credits in, we'll double whatever you put in there. So you can start building your own AI-based or data science-based applications. And I'll take any questions if you have them.
Okay, I have a question, Foka.
Yeah.
So how can you ensure the security? Like you were talking about how OpenAI is not secure. How can we ensure what do you guys do to ensure the security of your solutions?
Well, there's a couple things. So when I say OpenAI is not secure, like the biggest complaint we've heard from people is just the usage of their data in the training of the next model, right? We don't store any of that data. So we don't train models. We don't train LLMs. We just use open source models that are available. And so there's no need for us to store that data. The other thing you can do, this is a little bit more expensive, is deploy your own LLMs. We're actually also working on a solution right now where we're trying to reduce the cost of running your own LLM, specifically around de-inferencing. We're not really touching the training component. Just takes a bunch of GPUs and they're super hard to get. And so we're mostly focused on the inferencing component where we're trying to reduce the cost of the inferencing itself. And the way we do that is by using a smart combination of the memory, the CPU, and the GPU, and then trading in latency for cost. So if you're not wanting an answer right now, but you can wait a couple more seconds, we can do that a lot cheaper and run your own LLMs. And that will definitely be a lot more secure than running anything through a third-party vendor. But yeah, like I said, the affordable way is just using open source LLMs, which we provide. But then again, we don't have any incentive to store the data there, and we won't.
Okay, great.
Abby,
Yes,
I see your hand.
Yeah, just a quick question. Great presentation, by the way, really insightful as well, just because I'm looking into projects like this. Just a quick question regarding your customer feedback and just kind of the kick that it gave you. Where did you initially see some like, hey, we need some help? I after that, you had some customers reaching out and with these problems. After that, what was your next kind of like, okay, let's improve here, and what are your some steps for the future, you think?
Yeah, that's a really great question. So I think I had a pretty interesting. So before I joined this company, I worked for a company called Inside Data Science, where we trained PhDs to transition into the data science industry. And through that program, I've interacted with close to 2,000 people, indirectly or directly. And really what I know from that is that a lot, like most companies require a PhD. No PhD program teaches you anything about infrastructure. And so every time those people went to an interview, they really, really struggled with systems design, with infrastructure, with anything there. And so we knew there was a little bit of a problem there. Once we started talking to them, it became more and more clear. Like I've heard so many like horror stories of building data pipelines. And one of my questions was, how long does it take you to go to production? And anything from like 12 to 18 months came up, right? And that's just crazy. That's crazy. You have a platform, you've got a solution for the data scientist, the models work, everything is there. And then you just get the bureaucracy of getting the right infrastructure. And it actually comes in two flavors, which I thought was pretty interesting. So it comes in the flavor of it's a more traditional company. So they have setups, they've got flows, they've got things where there's a cloud setup that you can use, but it's all CPU driven. It's all web application driven. And so you show up with a slightly larger model that can run on CPU, or you're shit out of luck. And then they start doing their own stuff. And this is where the real problems start, because if you got a, say, a team of like 10 people, right? Some have experience with AWS, others with GCP, others with Azure. Are you going to train them and put in that time, which is like, if I heard from people correctly, it takes anywhere between 2 to 3 months to get to a level where it's usable for the company? Or are you just going to let them do their thing, and then you get a hodgepodge of different cloud infrastructure, and then, well, you're technically multi-cloud, but it's not really by design. It just happened to be that way because people are more experienced with it. So I think that's really the problem that we want to solve, and that's the initial feedback we got. Long term, I think there's a couple ways where we want to go. I think we want to keep focusing on data science, but there's a lot of other industries that can benefit from this as well. I touched on it a little bit already, the LLM solutions. I really think, and we really believe, that LLM cost for inferencing is going to be a big problem in the industry. Nobody's really noticing it right now because the total cost is low, but the total cost is low because they got 100 customers on it, because they're all super early products. They just got a couple beta testers on it, but the cost per user is incredibly high. And if you look at, I saw a tweet, like I thought it was last week, somebody was like, hey, it was kind of satire, but he was like, I'm trying to cut down on cost for my startup. I pay $50 for Google, for my Google Apps account. I pay $150 for Notion, and I pay $12,000 for OpenAI. Where can I cut cost? Well, I think you can cut cost at $12,000 if we can start trading in the latency for the cost there. And I think, honestly, most solutions, and I'm not talking about minutes here, right? I'm talking about seconds. Does it really matter if you get a reply right now, especially for like things like chat agents? I mean, if I'm talking I was actually talking to an AWS or an Amazon support agent this morning. It takes a couple of minutes to get an answer because they're talking to 10 different people. Does it really matter if it's going to take 3 seconds to get your answer? I don't think so.
And it's more
so I think
fidelity focused there as well. You're looking for a strong answer that actually responds to the question.
Exactly.
So I think it's a race there. I agree on that front too. I also agree that it's a huge race and a trend to make sure that it's cost effective and even now sustainable. I think that question is becoming even more present. And I think that it's very interesting how you kind of are trying to tackle some accessibility within this industry. It's really cool to see. So thank you.
Yeah. Absolutely. Todd, I see another hand.
Yeah, can you just list the bare metal providers that you're using so they'll be in the video?
Oh, yeah. Equinix, I believe it's high velocity, and OVH, I believe. I'll look it up. If you send me an email, I'll
Oh,
send you the actual
that's
stuff. But
good.
yeah, I think
That's
that's
good.
the ones that we're using.
I got a couple, so I know where to look. Thank you.
Yeah.
Foka, what role does LangChain play in
Ooh.
your startup?
Good question. So, and I say good question because this, I don't know if you guys saw that thread on the Reddit the other day, and then subsequently on Hacker News about what the benefit of LangChain in production environments is. We are building integrations with LangChain. And so the vector store that we're using will be integrated with LangChain. The models that we're building will be integrated with LangChain. I've heard a lot of complaints from people that it doesn't scale. So we'll have to see how that holds up. I've also heard some complaints that it might be just making like as a wrapper around like very basic functions in Python. Truth of the matter is that it helps people to build chat apps, build LLM-based apps. I think there's some value in that. And we'll have to see how they transition into productionalizing that. But yeah, we're going to integrate with them for now and just see how things go. But I think they're market leader essentially in these chat spaces, especially for the mid to like startup mid-level. I've talked to a lot of startups that actually took the code to production and don't seem to have any issues with it. So definitely going to integrate with them. I think there's it just speed things up so quickly, right? I'm building a demo app myself right now, which is an extension of this that allows you to chat with PDFs. And so ask questions about, okay, what's in that PDF? We're gonna use that there. I think there's just a lot of value there. But definitely a good question. And it's something I've been spending a lot of time on last week, trying to understand what the complaints were. If anybody has any like insights into that, like I'd love to chat, see why it worked or why it didn't work. Definitely interested in hearing that.
Any more questions for Foka?
All
Okay.
right. Well, thank you all so much.
Actually, Foka, before you go, I wanted to give
Oh,
you
I'll stay. I'll stay on.
Yeah, before you go, I wanted to give
Yeah.
you a compliment. You know, I read this book called The Lean Startup, and it talks about how startups are usually a bunch of brilliant people creating a product that they think everybody will use, and they never get feedback, and then the product fails. But you and your company have done more market research than I've ever seen anybody do. You've been calling hundreds, thousands of people, asking them what they need, and I think that's really special. And I wish you guys
Absolutely.
the best of luck.
Thank you so much. I appreciate that. Yeah, it's been if we added up all the calls, I think we had about 1,000 hours of or no, I'm saying that wrong. 150 hours of calls, and it's a lot.
Yeah.
But you know what's fun? If you start to see the patterns and you're like, wait a second, that's a big problem. So there's a lot of unsolved stuff. So if anybody is interested in building anything, I would definitely look into the data science space because there's a lot of pain points. People would just not stop talking to us. 30-minute calls turned into an hour and they were just complaining.
Yeah.
which is great if you're building a product. So definitely thank you so much. Appreciate it.
Okay. Thank you, Foka. All right. So our next speaker is Todd Bezenek. And Todd is a very well-educated person. He has 2 bachelor's degrees and 2 masters in electrical engineering and computer science. And he has some very controversial ideas about artificial intelligence. So Todd, why don't you take it away?
Yeah, thank you, Tyler. Can you, Tyler, can you see my slides okay?
Yes.
Okay, and you can see my whole screen?
Yes.
So okay, perfect. So I know I'm in the right place because Faki, did I pronounce that right? He has an espresso machine in the background, and everything he said was very simple. All of the code was simple to understand, and many questions that I had were answered without me asking them. So here's my talk. it was why AI is the locomotive of the 21st century, but that talk's already been given. You can find it easily. So my talk is now called, Is This Stuff Safe? The password for the PDF that's going to be available, you'll find out where to find it. You won't be able to find the password, so write that down. And if you have a question, be ready to say something, and only if you have an answer, you know it's correct. Sorry, only if you have a, what did I say there? If I ask a question, be ready to say something, please, but only if you have the answer and you know it's correct. Or if you have a stupid question. I won't answer questions that aren't stupid. So Tyler, be ready to unmute. Now, most talks that are being given for the first time run too long, so I'm going to rush. So the slides are going to be available at omnifitus.xyz, but the site's not up. I paid somebody to host the site and it's down because they messed it up. So I started using my 4 MacBooks seriously about 3 weeks ago. I'm still learning. This is my first Apple Pages document that you're looking at. I started working on it yesterday. The fact that this is so easy to do is amazing. My expertise is in computer architecture. At one time, I was in the top 1,000 people in the world. I can say that fairly confidently. My other specialty is virtualization, virtual machines. I'm working in supercomputing technology and data science right now. So over the past 3 weeks, I've been doing 2 things other than trying to get my website back up. I've been thinking about, where's technology converging? Where is it converging in terms of the processor we're going to be using, the operating system we're going to be using, the applications, the storage, the human machine interfaces? Is the operating system really going to be a hypervisor? Things like that. And I've been looking, what are the most powerful websites and companies in the United States and or the world? And now I've got a whole bunch of notes to myself, and I'm not going to remember what they all mean. There are things I want to go through quickly. So one is, I got a lot of comments on this. I can't see myself right now, so I hope it looks good. That's Van Gogh's Starry Night. A lot of people think he was suffering from a mental disease that caused him to see things in a different way than other people do. Oh, and when I interviewed at Facebook to be a performance person, the person that interviewed me thought this was really cool, and so did the security guard at the door. And that's a MacBook. So let's see. This here, I got this when I worked at MIPS. It is actually, I think we gave these people for free. It's actually got software to help people use the MIPS processor. And for some reason, today we're using RISC-V. We're not using MIPS. I find that very interesting. So I've got a Walkman here. I just dug this out this morning. Why are we using iPods and not the Sony Walkman? Very interesting. I've got this hat. I got this yesterday at Google. If anybody knows what this logo means, please tell me. Because the guy that was wearing it, he worked in fintech, and I did a search for this logo online this morning. I can't find out what that company is. So I've got one more thing I want to show you. I'm going to skip the customer truck Minneapolis thing. Well, now I'll say it quickly. This guy said that he was in Minneapolis and he turned down a dead end, and he was terrified because he was in a drug area. He got out of the drug area by pretending to be a customer because they treat their customers well. So I found this out 2 days ago. You can see my cursor over here on the left. If I do this, my cursor just went over and now it's on the screen of my MacBook Air. And I can type over there using the keyboard on this computer, on this computer. See, my cursor's moving. Isn't that amazing? That software was open source, available for free when I worked at Quantum 10, 12, 13 years ago. And now I can get it on my Mac. Onward and upward. So this is what I learned while I've been bumming around Silicon Valley trying to find out what I can learn about AI. Let's go through these things. This is the first one. I think it's the first one. Yep. So this is Maureen Dowd. She's an opinion person at the New York Times. I pay for their content. And she is talking about the strike that's going on right now. And that's Mr. Odenkirk. He's that really famous guy on that lawyer show, you know, Better Call Saul. I haven't watched it. And she said something really interesting here. Where is it? I wanted to highlight it, but oh, here it is. So on MSNBC's Morning Joe, somebody said, you can say, you know, here's the social network script. Write me a script, but make it about Elon Musk, not Mark Zuckerberg. And I guess they say it'll just happen, you know, because they can take images of Mark Zuckerberg and he could star in it. Yeah, but anyway, oh, and this is really cool. Jaron Lanier, I actually met him. I'm not going to tell you where. After he gave the talk, he said, now I've got to go do the thing I hate. I've got to go eat with the people that paid me to be here. But anyway, let's go to the next thing. So can somebody please let me know that everybody can hear me okay?
Yes, we can hear you.
We can hear
Great. So we're going to watch this whole thing because I don't think this is really scary. I think it's really obvious. But at the end, there's going to be a real person. The guy that's on stage talking about his company is an actor. So let's watch it. And I'm going to grab something to drink while it's playing.
Todd, do you want to make the video full screen?
Oh, yeah.
Did almost 3,000 precision strikes last year. We're super proud of it. It allows you to separate the bad guys from the good. It's a big deal. But we have something much bigger. Your kids probably have one of these, right? Not quite. Hell of a pilot? No. That skill is all AI. It's flying itself. Its processor can react 100 times faster than a human. The stochastic motion is an anti-sniper feature. Just like any mobile device these days, it has cameras and sensors, and just like your phones and social media apps, it does facial recognition. Inside here is 3 grams of shaped explosive. This is how it works. Did you see that? That little bang is enough to penetrate the skull and destroy the contents. They used to say guns don't kill people. People do. Well, people don't. They get emotional, disobey orders, aim high. Let's watch the weapons make the decisions. Now, trust me, these were all bad guys. Now, that is an airstrike of surgical precision. It's one of a range of products. Trained as a team, they can penetrate buildings, cars, trains, evade people, bullets, pretty much any countermeasure. They cannot be stopped. Now, I said this was big. Why? Because we are thinking big. Watch. A $25 million order now buys this. Enough to kill half a city. The bad half. Nuclear is obsolete. Take out your entire enemy, virtually risk-free. Just characterize him, release the swarm, and rest easy. These are available today. We have a distribution network taking orders from military, law enforcement, and specialist clients.
The nation is still recovering from yesterday's incident, which officials are describing as some kind of automated attack, which killed 11 U.S. senators at the Capitol building.
They flew in from everywhere, but attacked just one side of the aisle. It was chaos. People were screaming.
You can see high windows, very small, precisely punctured to gain entry to the building. What did you do for the victim?
I just did what I could for him. Things weren't even interested in me. They're just buzzing.
Government sources admit the intelligence community has no idea who perpetrated the attack, nor whether it was a state, group, or even a single individual.
So if we can't defend ourselves, then we strike back.
We are investing very heavily in classified defense projects.
We make it our deterrent like our nuclear deterrent. We stop.
I think I recognize the young lady on the right. I think she's an actress.
Pile in the millions, the billions.
At key facilities, the White House, the New York Stock Exchange, Wall Street. Well, we wish we had boots on the ground in every community in this country, but we don't. So our instructions,
Ollie?
our suggestions are to stay in touch with
Ollie, oh, hi. Hi, Ollie, honey. How's Edinburgh today? How are all your studies going, huh?
Good. Great.
Oh, great. Hey, aren't we doing a video call today?
I'm kind of with people, so.
Oh, well, come on, Oliver, put her on.
Oh no, it's not like that. No, wait.
Oh, well, listen, I see some photos here with somebody and I can see lots of likes and what's that all about? Oh, shit, here, it's on your mom.
It's on the spy stuff in the military.
What? What is this video right here? Oh,
No, I'm not going to click on
Oh, it's just this human rights thing about oppression or whatever.
honey, you're not going into politics, are you? I mean, no.
Safe here, just like you said it would be.
A720 this morning.
Police are not saying this morning what prompted the alert.
Claim relaxing firearm legislation would be useless against the so-called slaughter bots.
Says to stay away from crowds. When indoors, keep windows covered with shutters.
Protect your family. Stay inside.
Oliver, can you hear me? Please listen to me.
Authorities are still struggling to make sense of an attack on university campuses worldwide, which targeted some students and not others. The search for a motive is apparently turning to social media, and a video shared by the victims exposing corruption at the height.
But it's far from surprising. The weapons took away the expense, danger, and risk of waging war. And now we can't afford to challenge anyone, really. It's not even the smallest fringe group or a crank.
Who could have done this?
Anyone.
Dumb weapons drop where you point them. Smart weapons consume data. When you can find your enemy using data, even by a hashtag, you can target an evil ideology right where it starts.
This short film is more than just speculation. It shows the results of integrating and miniaturizing technologies that we already have. I'm Stuart Russell, a professor of computer science at Berkeley. I've worked in AI for more than 35 years. Its potential to benefit humanity is enormous, even in defense. Allowing machines to choose to kill humans will be devastating to our security and freedom. Thousands of my fellow researchers agree. We have an opportunity to prevent the future you just saw, but the window to act is closing fast.
Okay, someone please say you can hear me.
Can hear you.
Thank you. So I'm going to say a few things really fast. I was working in AI in 1993. I've seen that little snippet one other time. Did anybody notice the Morse code? Don't answer the question. It's not a question. I noticed Morse code. The letters SW were in there. My wife is going to Edinburgh. First vacation she's had in over 10 years. She's going in about 2 months. I'm not going to tell her she can't go just because I saw that this thing was in Edinburgh. I was going to invest in Zoom on yesterday because of something I heard. Today, I'm not going to invest in Zoom because of something I saw on the web. I think Zoom is in big trouble. Let's go to the next thing. This is something that I saw on the New York Times. I pay for the New York Times. This is the copy on my computer that I paid for. And whoops. Phooey. The links are the same. Let me find my copy. It's going to take too long. Trust me, I have a copy on my computer and it looks almost exactly the same. And because I paid for it, I'm going to keep it for the rest of my life. This is really cool. Like 17 or 18 people that work for the New York Times, they wrote, how do you think about America based on a movie you've seen? This is the movie that's most important to me. Scarlett Johansson played an AI that this guy fell in love with. And this one's interesting because this person looks like one of the floating in a vat of liquid on board a Cylon starship, people that was in the Battlestar Galactica version that was the good one with Mr. Almos, who is an amazing actor. And I've seen that twice, and it's just a TV show. It's amazing. Well, we got to move on. Let's get the distraction off the screen. And go to where my home is. That's my home. So AI is not safe because we just saw that. We know it's not safe, but it is safe. I'm going to read this. To make AI safe, ask it to tell you where to look for the answer instead of having it tell you the answer. You can have it tell you the answer at your own risk in free countries like the United States, where you get to make your own choices about what's safe and what's not. So the example I give people is, if the AI tells you that the answer is on the sidewalk outside the building, and you decide to get there by getting up from your 42nd floor desk and walking out the window, that's your problem, not the AI's problem. Any questions? Awesome. So I'm Todd Bezenek. I'm the engineer at large at omnifidus.xyz. The company is actually called Omnifidus. I have a whole bunch of acknowledgements to give because almost no one can do anything transcendent alone. Once in a while it happens. Mr. Einstein did something. So first, I'd like to thank the Academy. That's the Academy. They have the Academy Awards once a year. I'd also like to thank Elon Musk and this icon that he made. This is an icon that Elon Musk uses as the badge. You know, LinkedIn has a badge and DuckDuckGo has a badge. The DuckDuckGo badge is right here. And it's right here. Look at Elon Musk's badge. Yeah, that's pretty amazing. Mr. Musk does some pretty slick stuff, doesn't he? So I'd also like to thank Jim Gray, who passed away. When he passed away, he went out on his boat to scatter his mother's ashes near the Farallon Islands. He was a database person. The United States government repurposed a satellite to look for his boat. They didn't find anything. And I'd also like to thank Conrad Lai. He was my boss at Intel Labs. I didn't know how important he was until just a couple weeks ago when I read his Wikipedia entry.
Todd, I'm sorry to interrupt you. Abby has a question.
Sure.
Oh yeah, absolutely. Thank you. Excited to ask. I heard that you had some supercomputing experience, and last summer I did a little bit of a dive into that and what it means for the bio industry. Just curious if you see or have experienced or even worked with some of the intersections between supercomputing and artificial intelligence, and where you might see that going.
Yeah, I'm doing that right now.
And are you able to talk about it a little bit? I'm just curious as to like what the nature of it is, like what you guys are problems you guys are trying to solve potentially.
So I have a product. It's called Wisdom. And I tell people that there was another product called Oracle. Oracle answered questions you already knew the answers to. It just found the answer, in the pile of data that it keeps. It's a database. Wisdom, my product, it finds answers to questions you didn't know you should ask. So I'm going to keep going through my acknowledgements because I want to get through them. I'd like to acknowledge the A people at Omnifidus, because Jim Gray, that's this guy. When I went to his remembrance ceremony, 5 people said the same quote. Jim Gray said, A people hire A people, B people hire C people. At Omnifidus, I'm pretty sure we only have A people. I'd also like to thank Apple for always answering the phone at 1-800-MY-APPLE, even on the morning of the 4th of July, just a week and a half ago, I called and I talked to a real person and they answered a question for me. I'd like to thank Robert F. Kennedy Jr. for being a very hardworking person and for writing the book that he wrote that I read cover to cover because I was recently in bed for 3 months with COVID and I had time to read the book. Normally, I wouldn't have had time. I want to thank Floyd Patterson, who died of pancreatic cancer. He taught me finite automata theory out of Kohavi's book. He not only taught the class, he expanded on Kohavi's work, and Kohavi wrote the book. I'd like to thank Grammarly, that's my AI assistant, for helping me with spelling and grammar. Now you'll see here, Mr. Grammarly or whoever's helping, this is Mr. Grammarly down here. This AI is a little confused and it's a little confused here. And there are a couple of places down lower. And I'd like to thank Frode Odegaard for letting me participate in an amazing thing. And he met me at the Four Seasons in East Palo Alto afterwards, and I got a free pen from the bartender. And I use it instead of one of my expensive pens because it writes just as well. And if I lose it, I can get another one for free. This is another person that's passed away. John Marshall, he diagnosed my anxiety disorder. When I got to Wisconsin, I knew if I was going to be successful, I had to finally confront this problem I had, and I did. And Mr. Marshall really understood it. He was the founding doctor of the Anxiety Disorders Clinic at the University of Wisconsin, the first clinic of its kind in the world. And I'd like to thank Bill Devane for talking to me, not about anxiety, but he discovered Anand something. It's a brain chemical that's the brain chemical that gets stimulated when you smoke marijuana. He's a very famous biochemist. I'd like to thank Tears for Fears for doing my favorite song. It's called Everybody Wants to Rule the World. I love that song. It sounds great. But be careful what you work for, what you wish for, because ruling the world is a lot of work. And I wouldn't want all that stuff on my conscience. All the people that would die if I were ruling, I don't want to do that. I want to thank Rudy Preston and Scott Keel, my two roommates in college, and their families who I both knew. And these people are the most important, except for, well, yeah, my wife is here. David Wood, Doug Berger, Rick Weems, and Mari Seiler for sticking with me all the way through everything. And finally, my mother and grandmother. Virginia Bezenek was going to be a high school teacher until she was diagnosed with multiple sclerosis and had to quit. And she got caught in the system that back then, once you were in the system, if you wanted to get a job, you would lose your financial support, your health insurance. So she could never get a job, and she should have gone and volunteered somewhere because her life would have been so much better. And Ethel Esham, my grandmother, for both of them, for teaching me how to learn. And Ethel Esham, I dedicate everything I do to her. The work that I did for Hennessy and Patterson, the computer architecture textbook, I dedicated to her. And I think I dedicated the work I did for Jim Smith's book on virtual machines that I also worked on. And one more thing, Ken Jennings would have won at Jeopardy, except Watson cheated. Watson's not going to have to next time, I don't think. And if you haven't seen this, take a look at it. This is the new Watson. I just discovered this a little while ago. And then Elon Musk. Oh, and this end thing, I put end at the end of all my documents because once in a while in VI, I'll delete the last part of my document and I won't realize it and I'll break something.
Todd, I'm sorry to interrupt you. We're almost out of time.
Yep, perfect timing. Any questions?
Does anybody have questions for Todd? Nope, I'm not hearing any for right now.
That's awesome. I answered all the questions.
All right. Thank you, Todd. I really appreciate you taking the time to present for us. Okay, Boris, are you here? Okay. Hi, Boris. So Boris Ivanovic is the manager of autonomous research at NVIDIA. If you don't know, NVIDIA is the largest maker of hardware for artificial intelligence. I met Boris when I was running a group at Apple, and I was very happy with Boris's ability to be really smart and come up with amazing ideas and explain them in simple ways that other people can understand. So thank you, Boris. Why don't you start your presentation?
Yeah, I'd love to. I just have to wait until Todd stops sharing the screen, and then I can share mine as well.
Okay. Let me share my screen, and then I'm going to stop the share. Okay, now try it.
Do I have to do anything? Is everything?
No, you're fine.
Okay, perfect. So let me know if you guys can all see this. So thank you very much for the kind introduction, Tyler. My name, as you said, my name is Boris. I'm a manager of autonomous vehicle research at NVIDIA. And today I am really excited to talk. I'm going to talk a little bit about in the weeds of autonomous vehicle, stacks and how the software is architected. But I think what I'm really happy to talk about is that actually right now the field is going through a little bit of a revolution in terms of the kinds of stacks that are designed, the kinds of architectures that are deployed and tested. And I think it's a really exciting time. And I think, coming from the AV world, this is kind of my pitch for all of you other smart folks to come and join us in the AV world and help really push this technology forward to the point where, we can make it useful and safe and deployable everywhere. So as the title says, I'm going to talk today about architecting next generation AV stacks. So before we talk about the next generation, we should probably talk about what things currently look like. So current autonomy stacks kind of look like this. They're modular. They have key components, including perception, like detection and tracking of other obstacles, prediction of where they will go in the future, and then planning and control, taking into account this information to actually move the autonomous vehicle through the world. Now, this is the typical structure taught, for example, in schools, and that many AV companies adopt, including, for example, the one that NVIDIA has been developing for at least a few years now. Now, key advantages of this architecture include its interpretability and reusability. However, it also introduces information bottlenecks, which can give rise to integration challenges when you later need to, put everything together. On the other hand, and more recently, we also have end-to-end architectures, which directly link perception to control, typically through a neural network. And they only implicitly encode these kind of key component-wise capabilities. So while they're relatively new, end-to-end stacks are actively being developed by companies today, such as these here. And some key advantages here is that end-to-end architectures, they typically remove these information bottlenecks that I mentioned earlier. And one can argue that they achieve a level of optimality that's actually better than modular architectures, which are otherwise based on like a rigid decomposition. Now, among other things, it's very difficult to make any sort of formal safety claims of end-to-end architectures. So it's definitely kind of there's no one solution fits all just yet. Now, given the current state of things, a natural question is whether we can design something that gets the best of both worlds. And in particular, what we've been doing, at NVIDIA and the group is we've been viewing modular and end-to-end stacks as kind of like the ends of a spectrum. And so the core question here is, what would something in the middle look like? And this is actually exactly what I'll be talking about today. I'll go over some of our latest work towards this goal of developing a differentiable and modular architecture for autonomous driving. which combines the reusability and interpretability of modular stacks and the performance and integration of modern end-to-end architectures. So without further ado, let's get into the key ideas and the main topics that I'll be discussing today. So first, I'll talk about how we can expand the flow of information between already differentiable components, for example, perception and prediction in autonomous driving. Then I'll talk about how we can optimize components with respect to downstream task performance. And then finally, I'll kind of step back a little bit and talk about evaluating and generalizing these kinds of architectures. And I'll present some of our latest work on realistic simulation and efficient domain generalization before finishing with some overall takeaways. So let's dive into this first topic. So like I said, modular architectures, typically they suffer from the fact that they have information bottlenecks. And to give an example of what I'm referring to, let's take a look at the very typical autonomous driving stack here, where we have some perception components that feed into, planning and control at the end, which actually moves the car. There's many sources of uncertainty that actually affect these. And one example in particular that I'll show here is detection. So here I'm showing like a little video of kind of objects that are being detected in a scene. And you can see how for some of these, they actually flicker quite a bit, or maybe there's uncertainty about where they are in the world or their size. And as you can imagine, this has like a really big waterfall effect on all the rest of these components within the autonomy stack. So as you can imagine, there's been quite a bit of research into characterizing this uncertainty, incorporating it, accounting for it. And, myself and my group, we've done some of this work. But today in particular, I really want to focus on some kind of very visual examples that highlight this kind of interface between tracking objects and then predicting where they might go in the future. And in particular, I'm going to be talking about how two specific kinds of tracking errors can really detrimentally affect things downstream and how we can maybe account for that and fix that. So to show visually what these errors look like, I'm going to show you how, so this is, a car is just driving through a scene. And I'm showing here some bounding boxes, like basically objects that were detected. And then I'm also showing temporally, every time the video stops, how there are mistakes in time as these things are tracked. And so the two most common types of errors that you'll see are fragments and ID switches. And so ID switches here is basically when you have two vehicles that, for example, maybe one passes by another, one occludes another, and then their IDs or their identities are switched. And so you couldn't tell if something went in front of the other, and so you just kind of flip the identities. There's also fragments where basically you have one object passing in front of another, which then creates like a break in the track of that vehicle. And then that also causes problems when you're trying to use that historical information later on. So now that we've seen kind of what these errors could look like, this is what it looks like in terms of their effect downstream on prediction. So on the top left here, I'm showing just a normal prediction. Basically, we have a vehicle that's been moving, just kind of finishing a left turn. And we can see the predictions that your prediction module can make are pretty reasonable. I mean, the vehicle is basically just going to continue driving straight. Maybe it will veer a little bit towards the left or right. That's kind of later on. The problem is if you have one of these tracking errors, these predictions now can kind of grab onto this erroneous sense of like, oh, well, it would, maybe there was a fragment or an ID switch. And so now it looks like you have a sharp velocity change in one direction. And now your predictions are way off screen. They're completely useless. And what we found is that actually these, when you have these kinds of tracking errors, they really detrimentally affect prediction. And you basically have increases in your error rate of like 10 to 30 times, which is, as you can imagine, terrible if you're driving, self-driving car. So one core question that we asked was basically, do we actually need to do this, core step of tracking something in the world? Like, do we actually need to have, these mistakes even enter? And so something that we investigated was basically, can we remove this step of tracking something and instead directly use this past information into our prediction architecture, which is predominantly based on transformers nowadays. And so we tried this. We tried taking this kind of affinity information in terms of like how similar objects are and how similar they've been seen to be in the past, pass this information as well to a transformer. And we saw that these kinds of prediction errors, when you have these, otherwise detrimental tracking errors normally, they're basically completely disappear when you use this type of a affinity-based prediction method where you don't actually need to use explicit tracking. So it's kind of, you can trust, at least nowadays, there are neural network architectures that can make these associations for you, and you don't have to explicitly do it for them, which is really excellent from our perspective. And I'm showing here a side-by-side comparison of this kind of original stack, which had the cascading error problem, and then ours on the right, which doesn't. And you can see on the left, they're all just parked cars that I'm circling on the left, but you can see how when you have these kind of errors in tracking, there's basically, erroneous predictions. You can see those little lines that emanate from the rectangles. You see those on the left and you don't see them on the right, which basically shows you that these kinds of errors don't actually detrimentally affect prediction when you when you don't have an explicit tracking mechanism. So this is kind of one idea where you can really just expand the flow of information between two components and actually save yourself quite a lot of hassle. So now I want to look a little bit downstream in terms of, when you do have, now you have some predictions, let's say, and you need to actually make motion plans that the autonomous vehicle can use to drive and move in the world. And so the reason why it's interesting to focus in particular on these modules is because some of them are learned and some of them are not learned. Like they're just hand-coded optimization modules, as an example. And so it's a bit of an interesting interface because, neural networks and classical components are kind of viewed differently. They're kind of viewed as two separate things, and at least in a lot of modern literature. So in order to investigate how we can actually combine these all together, we started with just a very standard architecture. We basically just had, a neural network-based prediction model, a motion planner that you will find, a standard motion planner, sampling-based motion planner, and then some type of optimization-based controller, which, refines the trajectory and gives you something that you can track very nicely. So when we take these, conventionally, these modules are developed independently. You have a prediction model that's trained from data in order to, mimic how humans, predict how humans actually move. And then you have these planner and controllers that are hand-defined, hand-tuned, etc. Now, the key feature of what we were investigating is actually how we can make these two downstream components differentiable and bringing their, gradient information upstream to actually inform your prediction architecture of where its errors are, detrimental for planning. And so in order to do this, we had to kind of make some relaxing assumptions. We had to swap out some different components that are otherwise non-differentiable, but really, long story short is that we can still perform the exact same tasks. It's just that there might be maybe a more probabilistic flavor internally to some of these components. So what differentiability, like I said, what differentiability of this entire architecture allows us to do is that we can kind of compute losses here at the end of the pipeline and then back propagate them through these otherwise handcrafted algorithms and then make, inform our upstream neural network of how its errors are, how its outputs are actually performing in a task-aware manner. So the way we did this was we defined some losses for each of these, now learning-based components. And then we basically trained this on a real-world data set of human motion of basically an autonomous vehicle. It's like an open source, public driving data set. And we basically asked the question, how does this overall architecture compare to when you don't have these kinds of differentiable components? And so we basically did, very similar comparison as before. We took a standard modular stack, which did not have, these kinds of differentiable components. We compared it with ours that does have differentiable components. And what we evaluated was two things. At first, we evaluated how this prediction model actually performs when it does have these kinds of downstream task-aware information. And then we also compared the overall, performance of the motion plan that was generated by the overall stack. And what we saw was that basically this prediction architecture, which, like I said, it's just a neural network that's kind of predicting where agents might go in the future. the prediction performance as measured by basically just the displacement error of the output of what it predicts versus what actually happened in the real world, this displacement error is basically the same, or at least it's within, standard error. And so here we're able to basically keep the same prediction performance, and yet our actual, final motion plans are much better. They're significantly better. And here, these kind of percentages are basically showing you how close in performance you're getting to like a perfect motion planner. And when I say perfect motion planner here, I'm basically saying a motion planner that actually has perfect knowledge of the future. Like there's no predictions being made. It can actually access everything that every other agent is going to do in the future, because again, we have a data set we can, just pull from the future and pass this information in to kind of measure performance. And we can see that, while the standard stack is maybe 70% of the way there, when you have this differentiability, it actually increases to 83% of the way there. And what gives you this delta, what's kind of really the core differentiator here, is that now your upstream model, your upstream neural network model is task aware. And so basically, rather than just, having predictions that are, let's call it like equally erroneous, it learns that there are actually some very important situations that you don't want to make mistakes on. Or, it learns that if I have to make a mistake, I can do it on the vehicle that's 75 meters away versus the one that's immediately next to me, as an example. So taking into account now, let's say we even, we take all these ideas into account and we design ourselves a fantastic, super well performing autonomous vehicle architecture. We have to now still measure its performance. And even then we have to still talk about, can we generalize it to, other cities that maybe we haven't, collected in our training set, or maybe we haven't already scouted out for autonomous driving uses. So the first thing I'm going to talk about is how we can actually scalably evaluate like a full-scale autonomous driving stack. So accurate and realistic simulation is in many ways the holy grail to accelerating this, AV development process. And indeed, in the past few decades, the autonomous vehicle research community has made tremendous progress in developing really realistic driving simulators. So starting with like the seminal car sim simulator in 1990, we've seen driving simulations with ultra realistic sensor and physics simulations, like for example, Virtual Kitty and Carla, among others. And then very recently, NVIDIA has also developed their own drive sim, which has photorealistic rendering and integration within like their broader Omniverse ecosystem. Now, we're still not ready to use these simulators to validate the end-to-end performance of a driving stack. And arguably the key missing piece is that the behaviors of the simulated human agents, like other cars and pedestrians, they're still controlled, unfortunately, by pre-programmed logic or very simple models. But, as you know, the real world driving behavior of other humans is much more complex, much more nuanced, and much more interactive. So to truly create a realistic driving simulation, we need to actually build similarly intelligent agents to generate realistic and human-like driving behaviors. And so today I'm going to talk as well about some of our latest work in, trying to build this out. So concretely, we've kind of identified 4 key desiderata for traffic models that are useful for simulation. Namely, they need to be high fidelity. So they need to be able to, synthesize agent behaviors that actually resemble real world traffic, and maybe even more importantly, resembling group behaviors, since you might have quite a few vehicles around you. They need to be diverse. So we want to generate a very wide range of realistic traffic patterns rather than just, always the same, few 10. They also need to be controllable. So of course, we want to generate a lot of situations, but we also care about some specific, situations more than others. And so we want to be able to take these kinds of traffic models and very particularly generate things that we care about. And then lastly, we also want them to be adaptive. So like I said before, we also need to talk about and think about generalization. So can we actually, if we develop some models, can we adapt them? Let's say we train them on data from Boston and Singapore. Can we now adapt them to driving behavior from Germany? Can we, generally generate realistic driving behaviors from in China or Australia or whatever, with all their local nuances? Now, while these are kind of things that we know we need to do, we also face a number of technical research challenges to actually developing these. So the first is stability. We need to kind of prevent any of our simulations from diverging away from reasonable behaviors. And I'll show you an example of what this looks like quite soon. And also, we typically also want very long horizon simulations. So, you know, a lot of times the data that we might collect or train on is maybe only 10 to 20 seconds long, but we sometimes might need to simulate something that's minutes long in order to, you know, really build out some type of interactive scenario, or really, you know, generate some lead up into the kinds of scenario that we're interested in. So as I've shown in previous slides, we definitely have a good idea of how to model human driving behaviors, at least for the purposes of like predicting where other agents will go in the future. And so the, you know, very immediate question is, can we just take exactly what we've developed before, these kinds of prediction models, and just directly use them to simulate agents and have them be interactive and have them be useful for simulation? The answer is not quite. And I'm going to show here on the left just an example of, you know, this is just real world collected data. As you can see, it's smooth, you know, I mean, nothing really to write home about. It's just kind of normal driving behavior. On the right, I'm going to show what happens if you take a, you know, even a state-of-the-art prediction model and you make predictions, follow it for a little bit, make more predictions, follow them for a little bit, make more, and basically just auto-regressively try and generate trajectories and actually, you know, simulate agent motion in that way. So as you can see, it's really not that good. And it's kind of very quickly, we generate some motion that's, I mean, basically completely garbage. And, you know, unfortunately, it's basically simulation is not that easy. And the fundamental reason why you see problems like this when you know, just take otherwise very strong models and deploy them is that neural networks are quite famous for having problems with compounding errors where, you know, like I said, maybe you generate a prediction for the first, let's say 3 seconds, but then there's always going to be a little bit of error in those predictions, even maybe 10 centimeters or 20 centimeters. And so, okay, now you move your car along this, then you have to regenerate predictions, and you know, this kind of cycle of, you know, those errors that you're getting, you know, slowly but surely compound, and then suddenly you find yourself in a different lane, rotated wrongly, and, you know, you get behavior like this, which is basically completely out of the distribution that it was trained on, and it's completely erratic in terms of simulation. And so something that, you know, we've had good success with in the group and just in general for simulation is actually separating out the two components of driving, which is identifying where an agent might want to go and separating that from how it wants to get there. And so what we've actually been looking at is developing hierarchical policies, where basically we have, so here I'm showing on the right, basically a prediction of the goal of where an agent might want to go in, you know, some seconds into the future. And then on the left, I'm showing you how we can kind of connect now point A to point B, basically where the agent is currently to the goal that we're predicting it wants to go to. And you can see now how the, you know, the agent behaviors are extremely stable. They're very smooth. They're much more realistic. And all we did was kind of separate out this thinking from let's just generate a trajectory, you know, solving both problems at the same time. And if you just separate them out into a hierarchy, you're actually able to get much more reasonable performance almost immediately. Now, the best thing about this is, you know, what I showed you was just videos where we're controlling one agent and basically showing how we can maybe simulate that behavior among other drivers just replayed from data. Here, I'm going to show some videos of where we're controlling all vehicles in a scene. And you can actually see that we're able to synthesize some very interesting group behaviors. And remember here, none of these drivers or none of these, you know, vehicles are taken from real data. This is all completely simulated motion. I mean, the only thing we took from data was like the map, you know, map layout. So you're able to synthesize very interesting, complex interactive behaviors, even if every agent is thinking for itself, so to speak. We can also generate multiple diverse simulations, even enacting, you know, scenes from the exact same initialization. And this is because there's a little bit of stochasticity that you can add into these policies. And so you can actually get diverse behaviors, even from the exact same initialization. Now, I'm showing you some, nice videos, and I'm claiming that the driving performance is great. But it is really an important question: is how can you actually evaluate simulation quality? And this is quite difficult because, we can't just use, there's no such thing as ground truth for simulation, because you're trying to simulate behaviors that you either haven't seen before, or they're different, realizations of how you can drive through an existing scenario. So there's no kind of data set that you can refer to and be like, okay, how close was this to the correct answer, so to speak? And so what we've also tried to do in the group, and what we're using in-house now, are kind of a suite of evaluation metrics that at least paint a picture of how, these kinds of simulations are plausible and realistic. And so we kind of have three classes of these. So the first is basically the lowest level, and we call these kind of rollout metrics. So here you can basically analyze like the individual trajectories that you simulate, and you can basically find, okay, what is like, how much area do they cover? How much diversity is there in repeated simulations? Like basically how different, is the actual, if you plot them all on top of each other, how different are they from one another? And of course, we can also ask, what are the failure rates? For example, how many collisions are there? How much off-road driving is there? How much high acceleration driving is there? Things that we kind of know a priori are not very realistic, or at least rarer than kind of just normal standard driving. So these are, what we call rollout metrics. Then we can also compare some statistical differences. So, although I said we can't really compare directly with real world data, we can at least maybe compare distribution. So we can compare, for example, the speed histograms, or the, acceleration histograms, or jerk histograms, and we can compare that to real world driving behavior. And, here we kind of want the differences to be very small, because it at least means that statistically we're able to reconstruct human driving behavior, at least in marginal statistics. And then the last thing we're looking at is, kind of the classic research answer is, can we learn a model that evaluates how plausible your driving is? Now, this also has problems of its own, because, you're now kind of 2 levels removed from, let's say, original human driving data, but at least, it is a direction that not just us, but others have also been pursuing. So as these models get better, maybe we actually will have, strong measures of how plausible a specific simulated trajectory is. Now, like I said before, we kind of have 4 desiderata, and so far I've mainly talked about 2, that is fidelity and diversity. Now, that model that I showed you, this specific one, bits, which, and just a quick aside, we can see, here, at least in all these metrics, it's kind of thrashing a lot of the other models. So great, we're very happy about that. But it's not very controllable, right? We can't kind of ask, no, I want to simulate specifically this vehicle in front of this vehicle moving at this velocity, and et cetera. And so to do this, we've had to, this was kind of the focus of another one of our projects, where you can ignore a lot of what's going on here. The only important thing to know is that, we've developed a diffusion model that can generate driving trajectories. And what we've been able to do is allow a user to specify like formal logic rules for how they want driving to, what kinds of rules they want these different vehicles to enact. And we've been able to take these rules, and when I say formal logic, it's in particular, they're specifying them in signal temporal logic language, which it just is a formal, logic system that you can use to define rules. And we've been able to take these, logical specifications and use them to guide kind of the denoising process within a diffusion model. And so it's actually a very explicit way to bring in, let's say, your desires for traffic simulation and have them affect the actual output trajectories. And so the quick example that I want to show here is, on the top, we just have normal simulated driving. It's just vehicles, moving, and I'm visualizing them here in NVIDIA's Drive Sim. So on the top, we just have normal motion. On the bottom, we've added specific rules to actually have these 3 specific vehicles stop in these locations. And what's nice is basically by having this guidance of these rules, these agents, they were able to kind of realize that they need to stop, so they slowed down earlier, and they basically had their trajectories perfectly ending up where we wanted them to. Now, I have to admit, formal logic and kind of mathematical formalisms, it might not be the most intuitive way for, let's say the vast majority of us who aren't like straight up pure mathematicians to enter, our desires for how we want driving behavior to be enacted. And so what we've also recently been doing in the group is actually turning to language as a medium for allowing users to specify their desires and, basically allowing kind of developing like a text simulation framework where we can then use powerful language models to encode natural language specifications of simulation settings. And these don't have to just be, user desired, like, generate something that, generate 3 vehicles moving in this way. We can actually use other text specifications, like, for example, police statements from collision scenarios. And then we can try and recreate those in simulation and see if our own autonomous vehicle stack would get fooled or would make a mistake or would actually end up in the same collision that otherwise 2 or 3 humans did in that report. And so what we do is we actually take these specifications, translate them into this kind of formal logic language using powerful language models, and then have the traffic simulation generation process be enforced by these rules. And so I'm going to show like a particular example here where, one of our latest models is able to factor in this exact instruction on the top left to simulate a scenario where 2 vehicles collide in this exact specific manner of, one vehicle hitting the left side of another vehicle. Now, here's actually like taking that police statement idea further. Here's actually some examples of this collision scenario reconstruction use case where we took crash scenarios that were recorded in the National Highway Traffic Safety Administration's crash database. And, I have to point out that all of these specifications they're actually text only. There's no images, there's no videos. Actually, all of these videos that you're seeing are reconstructions by our simulation model. And so the great thing about this is that, otherwise, this database of crash information and collision information is kind of inaccessible for a lot of researchers or engineers. But now we can actually harness them by converting them with our text simulation framework and immediately using these trajectories to, evaluate things. We're also exploring some ways to, like I said, we can also generate traffic scenarios just, from freehand text. And so I'm showing some examples here of how, if you want to generate different densities of traffic, you can simply, write what you want. And I'm showing on the right kind of the outputs in terms of the density of traffic from, your free-handed user instructions. Now, beyond just a one-time, this kind of initial scene generation, we can also enable editing of the generated scenario. So, let's say you generate like a crowded scenario, but maybe, what I showed back here, maybe this is a bit too boring, right? Because it's just straight driving or something like that. Or maybe in this example, you asked for the generation of some 3-way or 4-way intersection, but it seems a little bit too boring. Maybe you want the car in front to actually turn left. Maybe you don't want cars that are kind of on the horizontal, at least, visually horizontal here. Maybe you want more density of vehicles on the left of your, of the lane of interest. And maybe you want to actually speed up, maybe it's the scenario is too slow and you want to have a bit higher velocity. What's actually very interesting about this last step is that when you ask, or like when you tell the model to speed up cars that are moving here in the same direction as the autonomous vehicle, it actually knows correctly to move this blue vehicle out from behind the red one. And this is interesting because basically, in order for all of these vehicles to be able to speed up in the same direction, it knows that this blue vehicle is not going to have enough space to actually accelerate and get a higher velocity because this red vehicle is kind of blocked up ahead. And so it actually correctly moves this blue vehicle to the right lane, and now it has kind of all the free lane ahead of it. So I think it's very interesting to see that actually these models, they're quite powerful in terms of even learning kind of these common sense patterns that you see in just normal, human driving traffic. So that's kind of the how did I say, the third of these desiderata. The final desiderata was generalization. So like I said, we have to, all of this is great. And maybe if your data is collected from all around the world, maybe actually your models are already generalized, but it's quite expensive to collect something from, all around the world. And so typically a lot of autonomous vehicle like software, designers and manufacturers, they only have data from specific cities or maybe even, a lot of cities within a state or something like that. But the real question is, how can we actually develop systems that can generalize to various driving standards that you otherwise don't even see in your collected data? So, what happens if you have different customs of driving, where maybe the density is much higher than you're used to? Or maybe there's different laws, like in Germany, if there's a traffic jam, you have to create a path through the middle because that's where emergency vehicles go. Or maybe there's different vehicles that you need to account for, like tuk-tuks in Thailand that you otherwise never see, for example, in North America or in Canada or in Germany or wherever. So one of the other projects that we've been doing in the group is taking a look at how we can actually take some of these models that I've shown you before and allow them to be adaptive. And in particular, we've been combining them with another recent paradigm in the machine learning field, which is meta learning, which is basically how you can enable models to very rapidly adapt to online observed information. And so I'm just showing an example here, like on the right, of just an example of what this might look like, where, maybe you have some function that you're trying to fit. And as you observe more data about the real function, you can see that your predictions like really snap to the correct answer. So this is just kind of like one illustration. But what this looks like from an autonomous driving perspective, so here what I'm going to show is the adaptation of a prediction module. So as you can see, it actually happened a little bit fast, but basically what happens is I trained a motion prediction model on a data set that had a very different, like a very particular data frequency. Like everything in that data set was collected 2 times per second. And so this model was used to data being collected at 2 times per second, and it was used to those kind of distances between waypoints and distances between positions and et cetera. But then I deployed this prediction model into another data set whose data was collected at 10 hertz, so 10 times per second. So as you can imagine, the spacing between waypoints is significantly shorter. And the density of data is significantly higher. And so what you can see in the very first frame of this GIF, you can see that the predictions are garbage. They're basically way overshooting, like, the kind of, like the length of the lane in front of it. And they're very fuzzy. You can see kind of these clouds of uncertainty. That's actually the prediction uncertainty that I'm visualizing. You can see this uncertainty kind of, flying all around on the right side. But then as it observes data online, and this is actually just about 1.5 seconds of driving data, as it observes data online, you can see that this uncertainty very quickly reduces, and very quickly the model learns, okay, this is actually how far apart, these different trajectory waypoints are, and this is how fast we're moving, and et cetera. And so it very quickly adapts to this new environment that otherwise it's never seen. Now, stepping back a little bit, when I was doing, when we do these kinds of projects in the group where we're going from one country to another, or one city to another, or one data set to another, you really realize how now is a fantastic time for AV research. Over the past, 3 or 4 years, there's been a ridiculous growth in the amount and size of public AV data sets that are completely open for researchers to use and to perform these kinds of, detection, tracking, prediction, or planning research and projects. And so the great thing is there's really a lot of public AV data sets that are available from many different locations in the world. The unfortunate thing is that each one of these kind of has a unique format. And so if you're a researcher, it's a little bit annoying because maybe, you're really happy finally you get to use, 1,000 hours of data and you can evaluate your model. But now you also want to check, okay, that's great. That's how it performs in American cities, but how can I see how it performs in Singapore? Or how can I see how it performs in Germany or Bulgaria? And now you have to, waste 2.5 weeks or 3 weeks, re-architecting your code to basically change, the input format that you're taking in because some other data set that you want to use has a very different input format. And so in order to kind of ameliorate this, for other researchers in the field, and I mean, even for ourselves, we've actually been developing in the group a unified data loader for actually autonomous vehicle trajectory data. So this is something that we've been using now for, I think, about a year. I mean, I forget the exact first day, but about a year now. It's fully open source, licensed very permissively. It's just Apache 2.0. And it's, you know, it's been accelerating a lot of our research. And I think, you know, if you're interested in the AV field or you're already an AV researcher, I really highly, you know, encourage you to take a look and to, you know, maybe try it out, and maybe it helps your research as well. And then lastly, you know, I showed a lot about our simulation work in this, you know, as I was going through this. And this is actually also another open source thing that we've released, I think maybe a few months ago. So actually a lot of these traffic behavior models or this traffic simulation, like evaluations and those things that I've been showing, you can actually try them out yourself as well. And we've actually, you know, combined the two framework, like that software framework that I showed in the previous slide. So, you know, if you want to try different traffic data sets and you don't just want to use one or the other, you can actually do this just by switching them within the unified data loader, you know, in a very few lines of code. So with that, I'm going to basically conclude here with some key takeaways. So, you know, I think that if you you know, ignore everything else, I think the core message I want to leave everyone with here is that autonomy stack components, and I shouldn't even say this isn't really just an AV specific, you know, piece of advice. It's actually true for any software that you write. It's not typically operating in isolation. You should really consider what are your downstream tasks, what things are using your software, what things are using your neural networks, and actually evaluate them with respect to that rather than just component level metrics. And actually along that point, if you do see some bottlenecks in performance, rather than increasing the performance of specific components, you should take a look at the interfaces between components. Because, you know, maybe as an example, maybe your prediction module gives you an excellent sense of uncertainty. But if your motion planner doesn't use that uncertainty, then it's pointless to improve it because you're never going to see any benefits from that perspective. And as I showed at the beginning, there's also really a full spectrum of architectural opportunities between, you know, these typical choices of classic modular or end-to-end architectures. And I think, you know, if you're developing something new, either in the robotics space, the AV space, or any of these kind of other related computer vision or machine learning fields, you should really keep that idea of differentiability and task awareness in mind, so that, you know, you don't kind of lose the plot if you're developing 7 components and then they're each optimized differently, and then your end performance is garbage and you don't know why. So lastly, you know, obviously in coming from the AV perspective, I think really closed loop simulation is really going to play an increasingly major role in the development of autonomous vehicles, in their verification, in their validation. And I think to really bring this kind of closed loop simulation idea into fruition, human modeling and accurate data-driven human modeling is really going to be a key enabling capability. So with that, I want to thank you all for your time and your attention. And I also want to say, if any of this is interesting to you, if you are interested in the AV field, we are hiring. So please, you know, you can just search kind of NVIDIA autonomous vehicle, fall internships, research scientists, senior research scientists, I mean, depending on your career stage, and we would be very happy to see your application. Thank you very much. I'm very happy to take your questions now.
Thank you, Boris. That was awesome. I really appreciate you speaking. We have a question from Abi.
Hey guys, great presentation. Awesome to get a look. I was looking into this at a hackathon back probably 2016, 2015, I want to say. So it was really interesting stuff back then. I think the first Waymo designs, I don't know if it was Waymo specifically, were being designed out. So we got to see the car looking great. And I think that it's awesome, you know, always had an interest in it. So 2 parts of this question. I'll keep it brief on both parts though. First is the ultimate trolley problem. Like, one is, how are you guys testing out ethics in this, and how does that come into play in your job, specifically being a manager? I'll just give you the floor for that one, because there's a lot of ways we could go for that one. I'm sure.
Sure. I love this question because it's a common one. And yet I actually think I'm going to pose it back to you. If our biggest problem is that an autonomous vehicle placed in like a 1 in a million scenario has difficulty finding a great solution, then we're doing fantastic. If you think about it, right? You put a human in a icy, slidey scenario, dark road, and it has to make it, and now you as a human, you have to make a decision. Do I oversteer more and go on the sidewalk, or do I understeer and maybe get lucky and only hit the car over there? We're hosed in either scenario, right? And so from my perspective, if really the biggest problem ends up being trolley problems, we are doing, as a field in AV, in like the field of AV, we are doing phenomenal, because I think it's like at that point we would have reached a level of reliability and safety that's like way above what I hope we need to really see widespread deployment and use.
So we're getting to that point as an industry, but still we're at the point where there's a lot further testing, a lot further implementations. And I really like the point that you brought up specifically with the tuk-tuks, because it's, whatever driving rules go. So that's a lot of variability that you could get a lot of information from. The next question is, for me specifically, from seeing it at that hackathon, had a lot of interest, have a lot of friends in the AV field. For like a absolute beginner, where's a good place to start? Because from my knowledge, there's no like absolute learning internships. There's no absolute like, hey, boots on the ground, just start learning here, at least at NVIDIA. So just curious, maybe you can add some of your experience there, how it was starting, but excited to break into that too.
Yeah. I mean, I think it's a great question, and I think it's very relevant for many people who have interest in this. I mean, maybe there are nowadays like autonomous driving courses, but I don't think there really are like that many autonomous driving courses, let's say at for example, universities, or at least in undergrad. And I think the way I started is basically I approached this I did my undergrad in electrical computer engineering, right? I was studying like literally power transformers, transistors, analog circuitry, whatever, right? And basically, in my senior year, we had like a thesis component, and I was taking a little bit courses just outside of that kind of electrical computer engineering front, and that was kind of where I discovered machine learning. And when I say discovered machine learning, I'm talking like literally like regression, classification, clustering, like nothing fancy, right? And so I kind of came into this field, and many people do come into this field from the perspective of computer science, machine learning. Computer vision is like another very common way you enter the field. And what I mean when I say enter the field is basically, so let's say now you've studied machine learning, you've studied computer vision, you understand maybe image classification, object detection, semantic segmentation, whatever. The cool thing is, and what I saw as well, a lot of these same tasks and problems you see in autonomous driving. So remember when I said, when I showed you in those videos that we're like detecting where other vehicles are. That's object detection. That's like straight up a computer vision task. When I was talking about motion prediction, actually, fun fact, a lot of things we use come from the field of natural language programming, or NLP, because it's literally a sequence-to-sequence prediction problem. I mean, sometimes it's like literally a sequence-to-sequence prediction problem. You're taking sequences of trajectory, like waypoints in time, or trajectories, like historical trajectories, and trying to predict future sequences of waypoints, or future trajectories, or distributions of them, or whatever. And so actually, a lot of people enter the field from this, let's say, from the machine learning existing big fields. And those are, I would say, much more wider spread, right? So that's at least one easy way. Another way, I mean, I was viewing this from like a purely, let's say, computer science or electrical engineering perspective, but as you can imagine, if you study mechanical engineering, you're already really close to the automotive world, and understanding dynamics of how vehicles move, understanding things like convex optimization, understanding things like motion planning. These are like robotics problems, and these are not just AV, right? You see them in manipulator design, like literally robot arms, or the KUKA arms that you see building cars in BMW plants. Like these are fields of study that have existed since must be the 1960s or 70s, right? I don't even know. So I would say you don't have to, if you're someone who's interested in autonomous driving, you don't have to like strive and yearn to find like, will Waymo teach me? Doesn't need to happen that way. And for me, it didn't happen that way. You can kind of learn these other, huge umbrella fields, and then you actually more easily see how things apply into different domains.
That's a great, awesome, great perspective and awesome way to put it, just because I think that, there's some things that I've already touched in this kind of list that you've given us too, which is really great to hear, just really comforting. So thank you for the answers and thanks for the guidance.
Of course. Thank you for the question.
All right, we have a question from Joe Lynn.
Go for it.
Hi. Sorry, my lighting's really bad, but I'm Joe. I'm an undergraduate sophomore attending UCLA and studying computer science. Thank you so much for the talk. I found it really informative and engaging. I actually had some other questions as well that you kind of like immediately answered in your next couple of slides. So thank you for that. So one of my questions was, I was wondering if you could elaborate a bit more on perhaps like modern approaches to analyzing like collision scenarios, because I know like there's been a lot of news about like Tesla's like crashing and whatnot, and trying to analyze like what parts of the model are actually causing issues. And I was wondering like how much does like the model architecture play into that, especially for like end-to-end models? Is it harder to like interpret where exactly in the model it's failing because it's hard to like interpret the I guess like the deep features of the model architecture, right?
Yeah, this is a great question. And I'll tell you, fun fact, I love the AV field because it's very easy to ask very hard questions. So your question is like literally basically hitting frontier of research already, because basically, actually, it doesn't really matter which of these slides I show, but basically it's like you said, when you do have, so Tesla actually is a good example here, because as you can imagine, they have like a very end-to-end kind of architecture, right? They show this in their AI day. They have this, these beautiful structures of basically just big neural networks, which in concert give you driving behavior. But if something goes wrong, it's very difficult to pinpoint where. Now, having said that, there are ways that you can mitigate kind of that uncertainty of where the origination of something going wrong. So something that you can do, for example, is have like auxiliary outputs. So let's say your original input is like camera images from the car. And then you can have like your output is, I don't know, motion plan that your car drives. You can also ask the model to give you, for example, detections of where other vehicles are, predictions of where they might go in the future, an estimate of, I don't know, let's say the cost function, like the cost values that it's using to plan or something like this. And basically you can do a little bit of introspection, even as the model's running, to basically do some like later analysis. Now, look, it's always trade-offs here. There's good things and bad things about that approach, right? Because even if you ask the model to give you, let's say, auxiliary outputs, there's no guarantee that it's actually using those auxiliary outputs in making its final decision and making its final outputs. So yeah, basically what I'm going to say there is like model analysis is actually quite I would say nascent, but I would say very fast growing field of machine learning research. And, there's a lot of this is where actually a lot of theoretical research also comes in, because you can try and identify, for example, a lot of problems in autonomous driving, they happen when you have out of distribution inputs. Like you see something that you've never seen before, and that now causes your neural networks to a little bit freak out, or they don't, they haven't seen this before. So they can produce some bad outputs. And there's ways that you can characterize this kind of stuff. And so there's even things that you can do theoretically that actually help you and maybe give you a little bit of guarantees in terms of like, okay, if I see something I haven't seen before, at least I might be able to identify it and maybe have a fallback policy or something like that, as an example. But it's a big open question, and I think it's a great, it's kind of nice, it's great to hear that, you're thinking about things like this, because this is exactly, I would say, one of the core research areas of autonomous driving nowadays.
Thank you so much.
Thank you.
All right, Todd, you have a question?
Yeah, I just wanted to say something. When I was doing my research at Wisconsin, I had an issue with colorblind people And there's actually a website where you can look and you can find out how colorblind people see your slides. So the red car, blue car, you know, whatever thing. And then I was interested, can you tell me, let's say that I have a Tesla and it's driving 30 miles an hour on a place where I would tend to drive 30 miles an hour. So it's probably, there's probably more energy used by the AI in order to be safe. So I'm wondering, you know, where's the sweet spot? What speed should I be going and I can be safe and I use the least energy? Because the AI is chewing up energy, you know, all the sensors and everything. And the car is chewing up energy, propelling me. You know, we used to like 55 because we saved gas, you know, and what's the sweet spot now?
Yeah, it's a great question. And actually, this is actually something that we talk about pretty regularly internally here, because NVIDIA also, I mean, as you might guess, also makes a lot of the hardware that's used for this, you know, computation on autonomous vehicles. And something that we talk about a lot is actually adaptive computation needs. So to give an example, if you are low speed, parked, things are moving slowly because maybe you're in a parking lot or something like that. Maybe you don't have to run something at 100 times per second. Maybe you can run it at 30 times a second, 10 times a second, 20 times a second, 15 times a second, slower rates as an example. Or if you're on the highway and maybe you're coming up to a, you know, California is very classic with these zipper merges or these like on-ramp, off-ramps after like 100 feet of, or like even closer than 100 feet, which is, you know, those are highly interactive scenarios. Maybe there you kind of need to kick up your replanning rate or your, let's call it your computation rate to 50 hertz or 100 hertz because, you know, there's a lot of things happening going on. It's high speed. You know, these are, as you say, a little bit more risky scenarios. And so I don't know that I can give you one number. Let me put it that way. I don't think I have one number, but definitely I would say it's per scenario, there are going to be different, let's say, computation frequencies that you can use, that like running this entire stack that you can use that give you basically the same performance and save power. From the like the AI perspective, the propelling side, you're always doing that. Yeah.
I have two quick questions for you, Boris. Number one, Elon Musk said that full self-driving is not possible until we have AGI. What do you think about that?
So,
what's AGI?
Full self-driving, it really depends on what that word full means. If we're talking a statistical level of full, which is usually what I take in my mind is like statistically, we are happy with, for example, the level of collision. It's, I don't know, it's 100 times less than whatever the National Highway Transport Safety Administration measures or whatever. I don't know. We can pick some line in the sand. I don't think that you need like straight up AGI. And the reason I say this is because I understand why Elon Musk would say something like this. I think from his perspective, I can see it, right? Because Tesla, they embrace a vision-only approach. You have multiple pairs of cameras, and you have to try and reconstruct the world. You have to try and understand distances of the world, and that's a very difficult computer vision problem. Many other companies, however, they're looking into using advanced sensors that humans don't have, right? So they're looking at using LiDAR to give you really accurate 3D understanding of the world. And when you have things like LiDAR, or you have things like radar, which can give you excellent velocity estimations, or really pinpoint, you know, other big metal objects around you, you're basically chopping away at the difficulties of the problem to the point where, like, for, you know, I always maintain in my mind, could be wrong, but I always believe that basically perception is kind of the most difficult problem within autonomous driving. Accurately perceiving the world in all lighting conditions, perceiving, you know, if you're coming up to a stoplight and you're going potentially 50 miles an hour on some roads, and that stoplight is like literally 2 pixels in like a high resolution camera. It was a stoplight like 2 pixels. Those are the most important 2 pixels in your entire, you know, 2K or 4K or 1080p image or whatever, and you have to detect those perfectly. And that's why I think perception, for example, is a very difficult problem within autonomous driving. And I think when you add in these other kinds of sensors that really help build this understanding of the world and help you, be able to piece together how the world is around you, then I think the amount of like surrounding intelligence, I don't think you need like an earth-shattering amount. You know what I mean? So look, I will be saying cautiously optimistic that I think we don't need something like AGI for autonomous driving.
Okay, thank you. And the second question was, I heard this week that pedestrians are stopping, I think, Waymo cars by putting an orange traffic cone on the hood of the car, and it just disables the car. Why does that happen?
Yeah, it's exactly the someone else who asked the earlier question is basically, you see a traffic cone directly in front of the camera. You've never seen that before in your training data, right? So this is like way out of distribution. So why does this happen? I mean, my guess is that the car has basically a safety fallback internally where it kind of knows, okay, I have not seen this scenario, and I know that currently I'm safely stopped at like 0, miles an hour. I'm just going to stay safely stopped. And, the car is not going to make any, risky maneuvers because it knows that its inputs they're wacky. It doesn't know how to interpret these things, or it doesn't know how to make, motion plans from this. So it just stays stopped.
Okay, interesting.
At least from, and I think it was Cruise vehicles, Cruise and Waymo vehicles, I think, in the city. And yeah, I mean, my guess is they're going to either train on this or they're going to come up with some other fallback policy. But I think that's basically what's going on. Yeah.
So that makes me think, if I'm in a situation where a killer Terminator robot is tracking me down, all I have to do is just something unexpected, like put a pod on my head or make a weird pose.
If you remember from a few years ago, there was a few people, for example, in the fashion industry, who remember when computer vision was really exploding in popularity. Facial recognition was kind of on the rise in terms of like, it was in the news all the time about how like governments wanted to use it, or like airports are using it, whatever. And I remember at the time that there was fashion designers who came up with adversarial patterns, basically clothing that you could wear, which had these very interesting, funky patterns that actually made you undetectable, or you had kind of, I mean, there's even simpler things you could do, right? You just have glasses with really strong IR cameras, IR lights, I mean, and then that also kind of saturates some camera things. So it's kind of like, yeah, there are, if you look out of distribution, that's good enough. So to speak.
Okay. Very, very cool. All right. Well, Boris, I appreciate you so much taking the time to talk with us. And Todd, I appreciate you too. Everybody, can we unmute our mics right now and give both of them a round of applause? All right. Well, thank you guys so much. This concludes the first meeting of Silicon Valley Artificial Intelligence Meetup. Thank you so much to our speakers, and thank you so much everybody else for coming, and have a great day.
Thank you all. Appreciate the talks.